That's not what these fields are supposed to look like. Just star fields, maybe a few galaxies here and there, right? So I was really horrified, like, oh no, what is that? And I quickly realized, oh no, that's Saturn. Oh no, I accidentally pointed the telescope at Saturn. I forgot to check and see that there weren't any planets passing through the field.
Let me welcome Sam Lawler. You're an astronomer at the University of Regina in Saskatchewan, Canada. You've also been educating the public about what those new satellite mega constellations are, what impact they're having on astronomy and on all of us. But the reason I brought you here is, and thank you very much for joining me for this. This is really exciting, especially for me as a photographer. Saturn has 274 moons. Just a couple of weeks ago, it had 128 moons fewer than that. How did this discovery happen, and what did you have to do with it?
Yeah. Okay. So a couple of my collaborators have had a targeted project on the Canada-France-Hawaii telescope to specifically find and track new moons of Saturn. And where I come into this is I have a program on the Canada-France-Hawaii telescope along with a large team of astronomers across the world to look for new Kuiper Belt objects. And so for this is called the Classy survey. And so what we're trying to do is look kind of evenly distributed points around the solar system and try to find the most distant and the smallest Kuiper Belt objects to learn about, is Planet 9 out there? How did the solar system form from these smaller pieces, right? So really, really neat science goals, right? And so we picked these 5 places around the solar system, and I very carefully calculated, okay, so here's the things that we found in 2022. Where are they going to be in 2023? Calculated exactly where to point the telescope. And the way the Canada-France-Hawaii telescope works is it's called Q-based observing. So I program in, I want you to look at this spot on the sky when the conditions are this good, and do this series of exposures, right? So I don't actually get to go to Hawaii. The
It's too
observers
bad.
who I know it is too bad. Logistically, it works out really well
So
because
so you so you
yeah.
give it a list of coordinates and
Yeah, exactly. And then they
filters and whatever to use.
exactly. And then there's expert observers at the summit who execute those programs when the conditions come up, and there's a priority, and it works great for Kuiper Belt studies. It's exactly what we need. So I carefully programmed in those points. Okay, where are these Kuiper Belt objects going to be in 2023? And then I look at the images as they come in the next day. And I was horrified to see, oh no, there's something really bright right in the middle of one of the fields. Oh
I
no.
think I have it
Um,
here. That's the picture you
yeah,
posted.
yes, yeah, exactly.
This does not look
So
intended.
that's not what these fields are supposed to look like. Just star fields, maybe a few galaxies here and there, right? So I was really horrified, like, oh no, what is that? And I quickly realized, oh no, that's Saturn. Oh no, I accidentally pointed the telescope at Saturn. I forgot to check and see that there weren't any planets passing through the field.
Okay.
So I felt really stupid. But then I realized that, yeah, my collaborators who are also part of the Classy team can use this data, and it worked out really well. This kind of filled in a hole in their data set, and they were able to track a few extra moons, get their orbits a little bit better with the data from me accidentally pointing the telescope at Saturn.
So Saturn photobombed your picture,
Yeah.
and the like drastic overexposure of what wasn't even supposed to be in there revealed some additional moons. Is that
Yeah, yeah,
correct?
exactly.
You know what?
So,
This is
yeah.
such a relief to see that astronomers who have trained for their entire life to be able to point a telescope to a specific point and then get the shot, that they have the same issues that us photographers have. This is
Yeah, exactly. I didn't expect a planet to photobomb my, right. This is millions of times brighter than what I'm looking for. So yeah, horribly overexposed, but the data are still useful for other projects. So that's
cool.
nice.
Just from a technical point of view, who decides the exposure for a picture? Like this is definitely, if you wanted to shoot Saturn, you'd have to have a much shorter exposure.
Oh yeah.
What what do you give the people out there who actually operate the telescopes? Is it just the coordinates and I don't know an exposure time, or is that a different information for different telescopes?
Well, I think it's different. It could be different for different telescopes. What a lot of the ones that I have used, yeah, you give them coordinates, you tell them how long an exposure you need, and a filter, right? So, what, because, so yeah, you can see this picture is just black and white, right? There's no color information in it. If you want color information, then you need to take several different filters, right? And combine that information
I think
afterwards.
here's one of my favorite ones. Where is it? Oh yeah, JWST
Oh
shot
yeah,
this one.
yeah,
This one of Saturn in near infrared
yeah,
with its NIRCam instrument, which yeah makes the rings light up like crazy. So
yeah, yeah,
the filter decides what part of the spectrum you want to see, and then
yeah,
in the end you
exactly.
might even go ahead and combine some of those pictures into a sort of color picture.
Yeah, but so we're with these the Saturn photobombed exposure, right? So we're trying to see so in astronomy we use magnitudes to talk about the brightness of stars, right? So magnitude 0 is like the brightest stars in the sky. Magnitude 6.5 is about the faintest things that you could see with your eyes from a very dark location. Um it's a logarithmic scale, right? So 6.5 is millions of times fainter than magnitude 0, right? So Saturn is like, I don't actually know off the top of my head. It's got to be
It's
about
bright.
magnitude 1, 0, right? It's very bright, right? The Kuiper Belt objects that we're trying to find in these exposures are like magnitude 26, right? So it's like way fainter.
Whoa.
Yeah,
So
yeah.
how long were
Um,
those exposures that you
well,
set up for
so
this?
yeah, so we do a series of 5-minute exposures, totaling up to 3 hours of exposure time, right? So we're really hammering on one spot. But the Kuiper Belt objects are moving relative to the background stars, right? So in order to combine all those images, you can't just add them together because the Kuiper Belt objects are moving, right? So we have to shift them at different rates and angles because we don't actually know where the Kuiper Belt objects are or exactly how they're moving on the sky. So we try many different rates and angles, and other people on my team are experts on at this, and it's very computationally intensive, but it lets you get to really faint limits with a smaller telescope. Like if you wanted to do that with a single exposure, you'd need like a 10-meter telescope. The Canada, France, Hawaii telescope is a 4-meter telescope, and we're able to, with a lot of computation power and clever setup of our images, we can get really faint limits.
So is that Saturn overexposure just one out of a whole series of 5 minute
Yeah,
exposures?
yeah,
So you could
yeah.
save the whole thing by leaving that out, is that correct?
Well, and so this is only a teeny tiny part of the image
I
also,
see, I
right? So
see.
the images are the camera is fantastic for Kuiper Belt studies, which is why we use it. It covers an area 4 times the size of the moon on the sky with each pointing, right? So it's great for this kind of survey. So Saturn only ruined like a little tiny portion of the image, and the rest of it all around Saturn is still very usable for science.
Cool. All right. So it didn't ruin your observations and it helped others
Yeah.
discover more
Well,
moons.
it wasn't ideal for our observations, but we could still use some of it around the edges, but it was perfect for getting in close and looking for these Saturn's moons. So, yeah, so it was still not great for the Kuiper Belt studies, but it ended up being useful for a different science project.
Which is cool. So your name is on those
Yeah.
moons. That's
Yeah.
awesome.
Yeah.
All
Yeah.
right. So the other thing, while I have you here,
Yeah.
in 3 years ago, I talked with astronomer Meredith Rawls from the
Yeah.
University of Washington, and we talked about mega constellations. I don't think they were called mega constellations back then. 3 years ago, this was a long time. A lot has happened, and we talked about the impact of these constellations, foremost Starlink, I guess, on astronomy and on other things. And in the meantime, I've been following you, and you are right in the middle of that topic, of
Yeah.
that aspect of things. So, can you give us a quick update on where things are right now? And
Yeah.
yeah, what's going
Yeah.
on?
Okay, so I would say just to start off, it's bad. It's really bad, right? It's bad for astronomy, it's bad for orbital safety, it's bad for those of us on the ground. The whole situation absolutely needs international regulation like 10 years ago. So in our data from this survey, we have watched the number of satellites in our data increase dramatically over the course of this 3-year survey, right? And so the way that it shows up in our images is in this 5-minute exposure, which we add up many of them to get 3 hours of exposures, depending on exactly where we're looking in the sky. Many, many satellites can fly through the field of view and leave a line through our image at different angles, right? And that's data that we lose, right? So it's effective. We just have to throw that whole streak away. So that's effectively making our telescope image smaller and smaller, right? It's making our science less effective. We need more time to get the same scientific goals. So that is across all of astronomy. This wide field imaging that I do is sort of the most widely affected, or most strongly affected by satellite streaks, but it's definitely affecting all areas of astronomy at this point. There are more than 7,000 Starlink satellites in orbit right now.
That's a lot.
Two-thirds of all satellites in orbit, two-thirds of all satellites in orbit are owned by one American private company owned by one billionaire, right? It's really bad. They effectively control orbit now. There's a whole bunch of other companies that are lined up to do the exact same thing. I'm quite worried about collision risks in orbit. I know that Starlink already does collision avoidance maneuvers every few minutes in order to not collide with other Starlink satellites and with debris, known debris that's in that very, very dense orbit that they're using, right? So I have lots of concerns about that. I've also seen debris from
You've been in the
SpaceX
media
spacecraft.
with big chunks
Yeah,
of black boxes and parts of satellites,
yeah,
parts
yeah,
of
like
vessels.
very, yeah, very large pieces. So the pieces that I have actually seen myself were from a SpaceX Crew Dragon trunk, so not a Starlink satellite. Um, and that fell just about 45 minutes drive from my house. And I just recently learned that a piece of a Starlink satellite was also found in Saskatchewan last year. So two SpaceX spacecraft fell on Saskatchewan within 6 months, which is it's just wild. And I think yeah, I've thought a lot about this. It's like, why here? Why Saskatchewan? That's
Oh,
so weird.
Saskatchewan's
But
big, isn't
yeah,
it?
Saskatchewan's big, and a huge portion of it is monoculture grain farms, right? So so these giant, like 10,000 acre farms that are completely plowed or harvested a couple of times a year, right? So big machines travel across huge areas of very flat, easy to search land, and so people find
So they
spacecraft parts.
these pieces
Yeah.
stick out pretty much. Yeah.
Yeah, yeah. But
Wow.
to me, the thing that's really worrying is that, okay, well, if we here in Saskatchewan found two of these, how many are across Canada? How many are across this whole band of latitudes, right? How many are in Europe at the same latitude, right? So we're at if you just make a plot of where all the Starlink satellites are, we between like 50 to 54 degrees latitude. That is the densest band of satellites, right? So this is where they're most likely to fall. So us in southern Canada and you in Europe, that's where they're going to land. And that's really quite worrying to me.
Also, the looking at the numbers, we are looking at tens of thousands of
Yeah.
satellites there, and my understanding is that they are sort of semi-disposable. They are like
Yeah.
planned to be up there maybe 5 years until the next round of technology replaces them. So, given those numbers, we probably have satellites deorbiting daily. There will
Oh,
be a daily occurrence,
yeah.
or is already maybe. I don't know.
Yeah, yeah. There were I think it was over 100 Starlink satellites that deorbited in January, right? I mean, it's huge numbers of them. When they're I mean, if you just do the math, right? So they want to have 42,000 satellites with 5-year lifetimes. That comes to an average of 23 satellites per day, right? That's
Oh,
almost a
okay.
satellite per hour that will be like put into orbit and burned up in Earth's atmosphere. And they say they'll burn up completely, but they already found a piece of a Starlink satellite here in Saskatchewan. So I have, having them burn up completely in the atmosphere is also a huge problem, right? Like these satellites aren't small. They're like the size of small trucks, right? So that's a lot of metal that's going to get deposited in Earth's atmosphere. And that's not we don't actually know what's going to happen. It's
Do, do,
really quite
do we
scary.
have any ideas what happens with all the materials that turn into fine steam up there or burn up
Yeah,
there?
metal
Because
vapor. Yeah. There's been
aluminum,
some
lithium, and stuff.
Yeah, there's been some studies that have started right, so this is atmospheric chemistry. I am not an atmospheric chemist. And there's some initial studies that said, well, it might deplete ozone, it might form alumina, which is like will change the opacity of the upper atmosphere. It's like the I've heard some people say, "Oh, well, that's great. That's like geoengineering, right? It'll cool down the planet." It's like, no, no, no. If we're gonna do geoengineering, it needs to be careful and well thought out, and well reasoned. Lots of experiments beforehand, not an accident of some other thing that we're doing, right? Like this is not the way to go about this. So the short answer is we don't know what's going to happen. The companies that are doing this they're just doing it. There's no environmental oversight. The US agency that regulates satellites has categorical exclusion for environmental regulations, so like they don't have to do anything. It's in space. It's Even though all of them will burn up in Earth's atmosphere, it's not considered legally an environment.
That's something you mentioned earlier about the legalities of this. I mean, I'm not a legal expert, but what's the current situation there? Who's responsible? Who
Yeah.
has oversight? I mean, we share space with everyone, so is there
Yeah.
a global authority that can do some regulation here?
There's the UN Office of Outer Space Affairs, but like they have very explicitly said that they're not in charge of enforcing regulations, right? Like that's not their job, and it should be their job, right? There's really nobody. It's up to each country that launches satellites to regulate them, which is dumb because they fly over everywhere else in the world, right? Like it's not like I see US satellites in my sky every night. It's not like they're restricted to only orbiting over whatever country launches them. So that's dumb. I know there are talks happening at the UN level, but meanwhile, Starlink is launching 60 more satellites a couple times a week, right? So it's just the regulation is so far behind. I don't know that it will ever catch up, which is scary.
Hmm. So how do we get out of this discussion with a positive slant?
Yeah.
It's
Well, I
hard.
mean, yeah, there's lots. So these satellites, Starlink, and all of these other mega constellations that are being proposed, it's for internet, right? It's for internet access. So if people have other ways to access internet or have ways to access internet from higher altitude orbits, they don't need to be this low. If they're such low altitude orbits, I keep hearing latency. Latency is important. But there's other ways to get internet to people, right? So advocate to your local government representatives for better rural and remote internet, right? I live on a rural farm. I'm lucky that I'm close enough to a city that I can access internet through a cell network rather than relying on satellites. But a little bit further out, there aren't any other good options, right?
Yeah.
So I totally understand why people are jumping on this, but SpaceX has never been asked why they need 42,000 satellites. Right? Nobody has ever questioned them on that number. So w- how do you do this with fewer, right? Like there is a limit to how many satellites we can have safely in orbit. It used to be that cell phone companies, each company had their own cell towers, right? But then they started sharing
Yeah.
infrastructure. Can we do that in orbit too? Like there's a limit to how much we can have there safely. So there are ways to make this much better. It's an engineering problem. So this is a challenge for engineers out there. How do you do this with fewer satellites and satellites that will last longer? That's the problem.
Right. So there are interest groups, astronomers first and foremost, because it directly impacts your research. What other interest groups are there who are advocating for the regulation?
Right now, not very many,
Not
right? Like
many, huh?
astronomers are really we're kind of the canaries in the coal mine here, right? Like we're
And we
the
need
first ones to
astronomy.
notice. Yeah, and this is making every part of astronomy harder, right? If nothing else, I worry about the discovery of near Earth asteroids, right? Like we showed with the DART mission, we have the technology to deflect a hazardous asteroid if we find it early enough, but all
Yeah.
these satellites are making that harder to do, right? It's incredibly important to have access to the sky, and culturally too, right? We've had access to the sky for as long as we've been human, and it's changing. You can't get away from light pollution from satellites. So astronomers are really leading the charge here, and there are many different groups. The International Astronomical Union has a group specifically dedicated to advocating for satellite regulation, and they've really taken the tactic of working with the companies, trying to talk to them directly, which is great. There's a group through the American Astronomical Society that's very active, also advocating for regulation and just educating the public, right? Most people don't know what's happening in orbit, so just telling people is also really helpful. Um, those are kind of the main big groups that are working on this right now. There's lots of smaller groups that are kind of starting up, but yeah, those are the biggest ones that I know of.
All right. So from discovering moons, from accidentally discovering moons or delivering data to a bit about how telescopes work to lower Earth um, orbit satellite constellations. Sam, thank you so much for your time, and maybe we can update this in a year from now and see where we are. Thank you so much.
Yeah, thanks for having me. Clear skies, everybody.